Okay, so welcome back after your lunch break. So this morning we're looking at organometallic reactions catalyzed by palladium, and in the two sessions this afternoon I want to look at reactions catalyzed by ruthenium, and in particular I want to look at metathesis for most of the sessions. So we will look at we will see examples of ring closing metathesis, cross metathesis, as well as metathesis more general. So just to remind you, we're now talking about ruthenium. We were talking about platinum. We're now coming 2 elements earlier in the periodic table and talking about ruthenium. This metathesis received recognition in 2005, and these 3 people, Yves Chauvin, Robert Grubbs, who's the man on the right, and Richard Schrock, jointly got the Nobel Prize for development of the metathesis method in organic synthesis. Metathesis had been used for many years as a very crude process in the oil and petroleum industry, but had not been tamed, you might say, for organic synthesis until these developments. The typical catalysts that are in use would be, three of them are shown here. These are not the only ones, but these would be three of the most common. The Grubbs catalyst, first generation here, you see it's actually a ruthenium carbene complex, and to be stable it's a complex with the phenylmethylene carbene. There are two tricyclohexyl pyridine moieties as ligands and two chlorines. The Grubbs second generation catalyst, which is more reactive, has actually an N heterocyclic carbene ligand instead of one of the phosphine ligands. MS there stands for mesotyl, so that's 2,4,6-trimethylphenyl, a bulky group. And then the catalyst developed by Grubbs and Hoveyda, where the carbene unit is actually tethered to a ligand which replaces, again, one of the phosphine ligands. So that's known as the Grubbs-Hoveyda catalyst, after the people who developed it. Each of these has its own particular properties. They gradually get more reactive as you go across. And there are plenty of others out there, but we can't look at all of them. What kind of reactions are we thinking about? What metathesis is doing is, if you take two alkenes, just imagine that there's an alkene, my forearm there, an alkene there. We will then join across the top and bottom, so you get two alkenes like that instead. So it literally is taking half of one alkene, half of the other, and joining them together. But if you put that into the context of organic molecules, let's take, say, ring closing metathesis, for example. If you have an alkene at one end and an alkene at the other end with some joining function, then you will actually, metathesis will join the two inner carbons together and the two outer carbons together. The outer carbons then will be released as ethene, and you'll form a ring with a double bond in it. That can be ring opened, and the ring opening will produce ends that can react with other molecules of themselves and give polymerization. But I'm not going to talk about polymerization in this lecture, or in these lectures. You can have ring opening, where you have a double bond in a ring, and you can have an external alkene, and if you imagine that lining up alongside the ring alkene and then chopping both alkenes in half, then you could have the CH2 here joined to one end and the R1CH joined to the other. So you're basically swapping over alkenes. You can do cross metathesis, which doesn't have to be intramolecular, and join two separate alkenes, and then you could get a cross metathesis product releasing ethene, and you can also get dimerization of each of the two individual alkenes, and we'll say more about how you control that later. So those are the kinds of reaction we're looking at. So we need to see how it works and then some examples of what can be done. Before doing that, I should say something about other catalysts. So you noticed all those the three I showed there all had Grubbs' name. Schrock, so Grubbs used ruthenium catalysts. Schrock in the same time was developing molybdenum catalysts, so here is one of them. The molybdenum catalysts are not as stable, which is why the Grubbs ones are the ones that are more often used in the lab. Generally speaking, these are more reactive, but not as stable. Chauvin's work was largely to do with the mechanism of metathesis. There is a tungsten catalyst as well that will deal with metathesis. For example, this one, which can be done by tungsten, it can be done by molybdenum catalysts as well, and that's to join these two alkynes together to give a new alkyne, and butane is the byproduct there. There is a titanium reagent, the TeBe reagent, which you can make from this dicyclopentadienyl titanium dichloride by treatment with trimethyl aluminium. Then going through this titanium aluminium mixed cycle, you can eliminate one of the aluminium residues and get a titanium carbene. And that can do metathesis with carbonyl groups. And so the group that is on the titanium ends up on the carbonyl carbon, and the group that's on the carbonyl carbon ends up on the titanium. So in some ways, you can relate what's happening in metathesis to what's happening in a Wittig reaction, where you're taking what could be regarded as a phosphorus carbon double bond and a carbon-carbon double bond, a carbon-oxygen double bond, putting the oxygen on the phosphorus and the carbon that was on the phosphorus onto the carbon that was the carbonyl group, so rather similar to this down here. But those are both using carbonyl as part of the metathesis. The ruthenium catalyzed ones deal with all carbon systems. So molybdenum works, and Schrock got part of the Nobel Prize for that, but in the laboratory nowadays, essentially it's the ruthenium catalysts of Grubbs and others that are most commonly used. So here are some processes that have been done. Here's one using the Grubbs first generation catalyst to form a double bond across here between the inner termini of these alkenes. The byproduct is the loss of ethene, and there would actually then be a double bond here, but this was then hydrogenated to give the single bond. Here's an example where Grubbs' second generation catalyst, the one with the NHC ligand, is used twice in this sequence, which is heading towards a marine natural product. But here's this double bond and this allyl group. If you join the inner carbon of this enol ether with the inner carbon of the allyl side chain, and again byproduct is ethene, you get this oxygen heterocycle with a double bond in. So the blue double bond is the one that's been formed in the metathesis. The same thing happens on the other side, because this is a nearly symmetrical species. So again, you form the blue double bond on the other side. If you then do modifications to build in new side chains containing a double bond, you can do, and these are not exactly the same as each other, these two sides, but you can do metathesis on both sides here. So if you join the inner carbon here to the inner carbon on the lower side chain, that's 1, 2, 3, 4, 5, 6, 7, 8. It's a 9-membered ring. The byproduct is ethene again. Shorter side chains, shorter chains on the other side, that makes a 6-membered ring. Again, yet again with ethene as the byproduct. So those are all examples of ring closing metathesis. So we need to have a think about what's going on here. So the catalyst starts out as a ruthenium carbene with some kind of substituent on here. In the Grubbs first generation catalyst, R is phenyl. So what happens? Don't worry too much about the other ligands, just think about the ruthenium carbon double bond as we're drawing it. Some other alkene can then complex to the ruthenium. The ruthenium can then lose one of its phosphine ligands, and we get a complex where the alkene is next door to the carbene ligand. And depending on the geometry of that complex, then you can get what is effectively a 2+2 addition. So the ruthenium carbon double bond adds to the alkene double bond to give you a ruthena cycle, a four-membered ring with ruthenium at one corner of it. And depending on the orientation that the alkene was in, you can either get a cis or a trans metallocyclobutane rutheno cycle. Various, you can call it either of those. Now the mechanism of that, it looks like a 2+2 cycloaddition. Whether it is concerted, no one really knows. And then that ruthena cycle can reverse, and it can lose the alternative alkene. It was made, taking this bottom one, it was made by making the two bonds drawn vertically on the board, but you could equally well break it down the other way, either side of the ruthenium. So it could go back to where it was, or it could split out a different alkene and produces a new ruthenium carbenoid that can go in at the beginning, and so this can keep going round and round. So generally speaking, how do you get out of this? Normally these things head towards the alkenes that are thermodynamically most stable, because these cycloadditions can go backwards and forwards, changing geometry, changing stereochemistry, etc., but you usually end up with what is the thermodynamically most stable combination. So the idea is alkene comes in, you get a 2+2, whatever the mechanism is, to give you a ruthenium carbene addition across an incoming alkene, and then that can break down either to go back to where it came from, or the other side of the ruthenium to give a new alkene and a new ruthenium ruthenium carbenoid. So a new alkene and a new ruthenium carbene complex. So let's think about that in terms of a ring closing metathesis. So here we have two alkenes joined together by some kind of connecting chain, with the Grubbs first generation, for example, which we will write, forgetting all the other ligands, not that they're not there, but just not putting them in for simplicity, as a ruthenium carbenoid with the phenyl CH carbene. The product you get then is these two ends coming together, the inner ends, and forming an alkene, and the two outer CH2s coming together and forming ethene. So what is happening there? Remember, the ruthenium carbene is only in catalytic amounts, small amounts. So the first thing that happens is one of these alkenes, in this case I'm not differentiating them, but if the alkenes are differently substituted, then the least hindered one will normally be the one where the first Ruthenius cycle forms. But anyway, a Ruthenius cycle forms, and then can lose phenylethene, which is splitting one of the original double bonds. So you lose this phenylethene or styrene. That gives you a new ruthenium carbenoid, but it's now attached to our full framework. That can then do another cycloaddition, another 2 + 2, to form a ruthenocycle, another metallocyclobutane, and now it's joining the two ends of the chain together. Now if that then splits in the opposite way to the way it was formed, you get a new ruthenium carbene, in this case ruthenium methylene, and the metathesis ring closure product. The ruthenium carbene can go back into the cycle at the beginning, replacing the phenyl substituted carbene, and because there's only a little bit of the styrene there, that only takes part in the first few cycles. After that, you don't need it. This, although it can actually participate in equilibration with the ruthenium methylene, so that can either go back and start its own cycle, or it can react with the styrene that's produced to give ethene and give the original carbene back. So all of those things are happening. But because there is only a small amount of the catalyst, you don't end up with that in this final product. So cycloaddition, which I'll call it that even though we don't know what the mechanism is, loss of the fragment that contains the original carbene to form a carbene on your chain that you're trying to do the metathesis with, another cycloaddition, another breakdown in the opposite direction to the way it was formed, and then you have a carbene to begin the cycle again, and you have the joined together metathesis product.
But the catalyst is regenerated?
The catalyst, well, this behaves as catalyst for the next cycle, or it exchanges with a small amount of styrene that's produced to produce exactly the same. So either this or this carry on the cycle.
But that reagent is consumed.
Sorry?
That reagent, the genium complex,
well, a ruthenium carbene is left at the end. Because if you look, all the carbons that are in here are here. So eventually you'll end up with ruthenium carbene at the end. Whether it's the original one or whether it's some of this left at the end, it's probably a mixture. But yeah, ruthenium carbene is regenerated. So using that general scheme, here are some other examples. This is a ring closing metathesis, and once again you'll see the innermost ends joined together to form a double bond. The byproduct overall is ethene. Although, as we were just discussing, there might be a bit of styrene in there as well, but just looking at the basic equation of this, it's double bond formed here, ethene formed, and you produce this 8-membered ring, which was needed en route to a marine natural product called Lorenzin. Now that's a ring closing, so the general mechanism I showed and this example are ring closing metathesis, RCM. You can do ROM as well, ring opening metathesis. So here is a fairly strained double bond. If you now use the same catalyst, actually number 1 there should say, it still is the Grubbs' first generation catalyst. I should have put the number up there. So the same ruthenium catalyst and ethene gas, then that does a ring opening metathesis. So each end of this alkene, then each end joins to half of the ethene. So you generate two new double bonds. Now, as I say, these are thermodynamics driven by thermodynamic stability, or you could have a lot of ethene present, so it's driven by Le Chatelier principle. But the other thing that's happening here is that this new product is set up to do a cope rearrangement. So if you count, it's 1, 2, 3, 4, 5, 6. So another factor that drives this forward from the ring opening is the fact that this cyclobutane here gets broken up in a cope rearrangement. And then you can see how that forms part of the skeleton of this, again, a marine natural product, whose name I can't pronounce. So the ring opening metathesis is driven by ring strain relief, and then that's held at the ring, that's prevented from going back or cross metathesizing with other molecules of itself by the fact it's designed to then undergo a cope rearrangement. So these metathesis reactions are pretty flexible in that sense. So what about cross metathesis? Rather than ring opening or closing a ring, where the two alkenes are held inevitably close to each other because there's a chain connecting them, what if you've actually got two completely independent molecules? Well, the Grubbs second generation catalyst is reactive enough to do, for example, this one, where you take this terminal double bond and styrene, and you can convert the terminal double bond into a styrene type double bond. So the inner carbon of the terminal alkene is joined to the carbon attached to the benzene ring by a double bond, and the two remaining carbons, overall, ethene is the byproduct. These are all done under the same conditions, using 5% of Grubbs' second generation catalyst, or of the Haveda catalyst, the Grubbs Haveda catalyst at the bottom. Here's one where this terminal alkyne, being the least substituted, is the one where the initial ruthenium carbene addition takes place, and that then reacts with this external alkene to replace the terminal methylene carbon here with the carbon carrying the ester group in your additional alkene. And here's a very similar one using the Haveda catalyst, doing the same thing. So the inner carbon here joining with the substituted carbon of the alkene. Now that looks great, but you're probably thinking already, what are the issues? Oh, here's the mechanism. We'll come on to the issues in a moment. I suppose let's comment. The issues here might be, how do you guarantee that you get the right combination undergoing cross metathesis? Well, we'll come back to that, but let's just look at the mechanism here. So this is an adaptation of the mechanism for the ring closing metathesis I showed earlier. So you've got two different alkenes, you want them to join together. You've got a ruthenium carbene catalyst. You can get a ruthenium carbene cycloaddition to one of the alkenes. You can break that ruthena cycle down the other way, so that actually will break one of your original alkenes. One carbon ends up with the bit that was on the carbene that was on the original catalyst. The other half of the blue alkene here ends up as a ruthenium carbene again. that adds to the second alkene. That could go cis or cis or trans. You get different orientations there. As I said several times, it'll be the thermodynamically most stable that you'll get, because notice these are all written as equilibria. And this new Ruthenius cycle can then break down across the horizontally, which is the opposite to the way it was made, produce another ruthenium carbene that can go back into the cycle at the beginning. You've got your cross metathesis product. The geometry will be determined by stability of the products, which means in a lot of cases, in a di-substituted alkene case, trans will often predominate, and then overall ethene byproduct. And the ruthenium methylene here, as well as taking part in the beginning of the cycle, could also equilibrate with the styrene that was released earlier on and actually give ethylene and go back to the ruthenium, the same ruthenium catalyst as we started with.
The closed metathesis reaction and metathesis reaction both with the same catalyst?
Sorry?
Both are closed.
Oh yeah. They will, yeah. It really, which catalyst you use depends on the reactivity of your system. So a number of ring closing metatheses, because the two ends are held together at the ends of a chain, will go with the first generation one. Not all cross metatheses will go with the first generation. May need the second generation. I'm not drawing that here, but the principle is the same. Even the second generation has a ruthenium carbenoid. It really is a matter of reactivity then. So gradually the catalysts have become more reactive as they've been developed.
Only difference of the substituents?
It depends on the substituents on the alkene, the situation of the alkenes, yeah. So most people nowadays would actually first try Grubbs' second generation catalyst, because that's a good compromise. They're all commercially available now if you've got the money, and the Grubbs one is, the Grubbs second generation it's reactive enough to do most things, and there are not many things it fails with. So whereas the first generation one, there are more examples where it's not reactive enough.
But ultimately it is the genium alkene that is going to react this part.
The ruthenium carbene.
Carbene.
Yeah, whether it's this one or this one or this one, or regenerate this one with the little bit of styrene, but there isn't very much of that. Yeah, it's the ruthenium carbene that...
So whether it is coming from first generation or...
Oh, well, yes, the difference is I'm not drawing the ligands here. So if you have the second generation one has an N-heterocyclic carbene ligand there, and the ligands do affect the reactivity of the ruthenium carbene. I'm doing that just for simplicity. There are still all the ligands there. I'm just leaving them out to simplify the drawing of it. But it is the ligands that affect the reactivity. So, but it's the ruthenium carbene part that is doing the reaction, and it's the surrounding ligands that are controlling the reactivity. Part of why the second generation catalyst is regarded as more reactive is because the N-heterocyclic carbene ligand is a better sigma donor than a phosphine ligand, and that is presumed to be why the catalyst is more reactive. The Grubbs-Haveda one has an oxygen donor atom instead of one of the phosphines. That's regarded also as being more electron rich. But I think those are arguments made after the event rather than arguments made for design of catalyst. So what are the issues with cross metathesis? Well, you've got two alkenes being metathesized, yes, you could get what you want, which is the heterodimer, in other words, metathesis between the two, but you could also get the homodimers, that is, each alkene metathesizing with itself. So how do you control that? Because all three of them, the mechanism would be the same to get there. Sometimes it's controlled by the stability of the three different alkenes, but you can imagine you need a little bit more knowledge to be able to control that. So the major issues are control of homodimerization and the EZ ratios in the products. You can't really see there, but those are there's a wavy line there. So it's E and Z mixtures are an issue. So Grubbs produced a paper in 2003, a table from which I'm going to show on the next slide. You won't be able to read it, but it shows you that you can go and look it up as to the best situations. So he took all kinds of situations, electron-rich alkenes, very hindered ones, 1,2 disubstituted, 1,1 disubstituted, singly substituted, electron-rich alkenes, and so on and so forth, just to see which combinations would work well. So one that does work well is where one of the components is an unsaturated carbonyl substrate, so an electron-deficient alkene, such as an alkene carrying an ester group. So that, in situations with the Grubbs 2 catalyst, the ruthenium with the NHC ligand on, seems to work, there it is. That's the opposite way. It's upside down from the way I drew it before. But that catalyst, and where one of the components in the cross metathesis is an unsaturated carbonyl substrate, that seems to work very well. As I say, you won't necessarily be able to read that, but this is taken from Grubbs' paper, which is this one here, 2003. This is the big table which tells you what happens, and it also tells you what happens with second generation, first generation, and the Schrock catalyst. So if you have terminal olefins with the Grubbs 2 catalyst, you get very fast homodimerization. Not a great plan, a good thing to plan into your synthesis. On the other hand, no homodimerization with a 1,1 disubstituted olefin and the Grubbs 2 catalyst. So you basically look through these here to find out what are good and what are bad situations. And there is enough known information out there now that you should be able to plan, will this work, won't it work? So for example, the alpha beta unsaturated or propenoic acid derivatives, acrylates, amides of acrylic acid itself, acrolein, which is propenal, vinyl ketones, so those are all alpha beta unsaturated carbonyls. They give slow homodimerization, so as long as the cross metathesis you want is faster than the homodimerization, you can get away with it. And at the bottom here are some things that won't undergo cross metathesis at all. And you can see the situation is different for the different catalysts. So you're looking for the right combinations. Now, no one expects anybody to remember that. You go look it up. But the one that I always remember is that the alpha beta unsaturated carbonyl compounds are good in cross metathesis because they only homodimerize very slowly. So if you do need to think about a cross metathesis, then obviously this is the place to go back to. And there may be, tables like this may have found their way into textbooks and so on by now, but this was the original table that Grubbs produced to try and help people plan cross-metathesis situations. Right, looks to me then that's the end of the first part for this afternoon, and we'll look at some other types of metathesis and some, what else was I going to, oh yeah, some gold activation chemistry in the next session. So we take a break now.
Is there any particular role of chlorine?
I don't know. You mean it as a ligand there? I'm not sure. I think you can go back to the early days when Grubbs was developing his first generation one, and I think if you read his early papers, you'll see. I mean, he came up, 2 phosphines in axial positions and 2 chlorines. I think there were others tried before that, but I don't remember what all the details were in terms of the development of that first generation catalyst. But I know he did investigate quite a number. I mean, in a sense, it wasn't clear in the early days whether ruthenium or molybdenum would be the ones to go for. But it turned out that this one turns out to be reactive enough to do quite a few metatheses, and this one's better. Whereas the molybdenum one is quite reactive, but not very stable to use in the lab. So I think it was just, in a sense, it was almost a chance that ruthenium beat molybdenum. And again, the reason for the exact ligands set here, I can't recall. But there are, apart from these 2, there are plenty of other variations there with different ligands there, which have slightly different reactivity properties. But these are the 2 that are most commonly used. So you'll hear people talk about Grubbs 1 and Grubbs 2, and that's what they really mean, although I've numbered that this opposite numbering to this. That's Grubbs 1 and that's Grubbs 2, so first and second generation. He's put this one as the first column here and studied it most because it's that little bit more reactive. Okay, short break.